Hey, welcome back. Today we're looking at 2.3 continuity. So a function is continuous at a point if limit as x approaches a of f of x is equal to f of a. So that's kind of like one of the weird things about math, right? The wording of it and how long it takes you to like read through it, understand what's going on. So the easier way to put this is if we plug in a number, or if we're finding the limit is the actual value. Okay, so the whole point here is if limit is the value, then it's continuous. So let's look at the continuity at all these points. So if we look at x equals 0, well, it's continuous at 0 because it's just a point. We can't go from the right and left, so we know that it's continuous at its endpoint because it's solid there. So this is going to be the limit as x approaches a for that one would be 1. Okay, if we look at the next one, as we approach 1 from the left and right, this one is not continuous. Because the left-hand side and the right-hand side are two different numbers. Right, so yeah, it doesn't have an overall limit, so therefore we can't have continuity there. Okay. For x equals 2, so the limit as we approach from the left and from the right, well, the limit is 1, excuse me, but the actual value is 2. So because the limit is 1 and the actual value is 2, they're not the same. It's not continuous here either. Not continuous. Okay. Now at x equals 3, let's erase all this other stuff. So x equals 3. As we approach from the left and the right, we see that it's equal to 2. And the actual value is 2. So this one is continuous. And then lastly, on the endpoint, well, we can only approach it from the right, and it's solid line. So this is also continuous. All right, so just some continuity things. The next page are types of discontinuities. Well, this one is not. This is what it looks like if it's continuous, right? The value is the same thing as the limit. Now, removal discontinuities, we saw one like this, right? The left side and the right side. We thought it was going towards this point. That was the limit. The limit was the hole in the graph, but the actual value was someplace else. And then same here. The limit approaches the hole in the graph, but there is not actual value, so that would be another discontinuity. We saw these jump ones, right, where the left and right don't connect at all. And then we have these infinite ones, so these are asymptotes, right? Asymptotes. There's an imaginary line here that our graph doesn't cross, but we approach infinity or negative infinity. That's why they're called infinite discontinuities. And then this is one that we don't see too often. It's oscillating. It's just like as we approach that value for our limit, it just gets kind of squashed up and like really pressed together. So it just kind of fluctuates. Yeah, so these top 4, well 3 actually, removable, jump, and infinite, are the ones we should be most concerned about. Those are the ones we're going to see most often. All right, so this time, rather than just talking about continuity at a point, we're talking about overall continuities over the whole function. So the thing with the continuity of a function that makes it funkier from just talking about continuity at a point is that they could mean different things. So let's look at the wording here. It says a function is continuous over an interval, right? Over an interval, if it's continuous on its own domain. Now, domain is underlined because that's the important factor here. So let's just kind of look at 1 over x. So if I graphed 1 over x, and you guys can do it on your graphing calculators or Desmos, what's going to happen is we're going to have a graph that looks like this. All right, so we have this asymptote at x equals 0. So the y-axis itself is an asymptote. Now, if we're looking at this and talking about this function, well, there's a break in the function. At first thought, we'd say that this function is discontinuous, right? Discontinuous, because there's definitely a gap between the left-hand side of this function and the right-hand side of this function. However, the whole key here is the part where it says domain. So yes, at the point x equals 0, this function is discontinuous, meaning that there's a gap that's easy to see. Now, the tricky part is that overall, though, overall, 1 over x is a continuous function. What? Okay, so let's talk about why it's a continuous function. So let's think about the domain. When we say that f of x equals 1 over x, right? We have this little disclaimer that says, oh wait, x cannot be equal to 0, right? X is not part of the domain of this function, because if we plugged in 0 there, we wouldn't have an answer. It'd be undefined. So 0 is not part of the domain. Therefore, even though it's discontinuous at 0, we don't include that. It's not part of the domain. So over the rest of this function, it's continuous. Right? So this whole domain thing here is very important to note, because the asymptote is not part of the domain. Everywhere else on this function, it is continuous. All right, so let's look back at the different types of discontinuities. Excuse me. So this one, right, depending on your function, would be continuous. Right? If that point there, if that x is not part of its domain, then it would be continuous. This one, though, would be discontinuous. Right? Because this point here is definitely part of the domain of the function, but there's a gap there. Okay? Jump would always be discontinuous. And then usually when we have infinite discontinuities, this would be continuous as well, because those asymptotes are not part of the domain of the function. So be very, very careful. Be very, very careful when we're talking about at a point for continuity versus over an interval. Okay, and then the interval thing, the whole thing is, remember that it depends on your domain of your function. All right, so theorem 7 says if f of x is continuous at c and g of x is continuous at f of c, then g composed of f of x is a continuous function at c. So it's kind of like a whole big thing, but what this deals with is composition. Remember when you guys were learning compositions and some of you were like, hey, when are we ever going to use this? This sucks. Well, this is one of the reasons why we want to be continuous. So we have this complex function, right? So it's saying, for example, y equals the absolute value of x sine x divided by x squared plus 2 is continuous, right? So let's say this is the inside. Well, what we know here is that this is continuous over the whole interval. And we know this because when we're talking about discontinuity, the bottom part is what we're mainly focusing on, right? There's no way we're going to get that to be a negative number inside of our in our denominator, because anything we put in there, positive is going to be positive, negative is going to be positive. We can't make this thing equal to 0, right? So we're good here. So this whole thing here is definitely continuous. And we also know that the absolute value function is also continuous. That's continuous. This is continuous. So because we have a function made up of a composition of two continuous functions, overall, they are continuous. Okay, so really simple, straightforward, something that's not difficult, not a difficult concept to understand, but now that it's out there and it's a theorem, we can use it to describe different things. Okay, intermediate value theorem. This is one of the big things in calculus. So, and again, it's kind of something that's intuitive if you think about it. You could probably have made this theorem up yourself in your brain, even though we might not have the math skills to prove it. What we know is that, let's say we have this interval from A to B, and our function is graphed here. So it says that if f of x is continuous, so again, right, the whole idea of continuity is very important in many of these theorems. On the interval from A to B, then it takes on all values between f of A and f of B. So let's say B was, I don't know, some arbitrary number, 100, and then A was 7. Right? Because this is continuous, that we know that at some point in here, we're going to have every value between 7 and 100. We're going to have 59, we're going to have 2, sorry, not 2, 27. We're going to have 53.1111111, because this is continuous. Each of those values is represented. Now, keep in mind, it just says between the value of A and the value of B. It doesn't include anything above, even though it could be, right? This answer could be 103, for example, right? We don't know anything about that, but we do definitely know that it's going to at some point find a value between 7 and 100. Okay, so let's say that again. Whatever the value is at the end and the value is at the beginning, the intermediate value theorem says that it takes on all of the values between 7 and 100. It's got to, because it's continuous. There's no breaks in the action. We're going to have the number in there somewhere at some point. Okay, so let's apply that idea here. So it says, is there a real number exactly 1 less than its cube? Compute to 3 decimal places. Okay, so is there a real number exactly 1 less than a cube? So let's say n is the number. And then let's say that the cube is going to be the number cube minus 1. So we're trying to find if there's a number n equals n cubed minus 1. Now we could go and do all the messy stuff here and figure all that stuff out, but let's use graphing technology here. So if you guys are comfortable using a calculator, what we're going to do is we're going to say that this is the one function and this is the other function. It's like a system of equations here, just written so that they're equal to each other. Whoops. So let's say one function is n, or in this case, let's say x, and then we're going to add another function, and that's going to be x cubed. Was it plus 1 or minus 1? Minus 1. Okay, let's find their graphs here. Whoa, that's zoomed way out. Okay, so it does look like they have an intersection, and that intersection is going to be at 1.325, 1.3247. 1.325. Now let's just round it, 1.325. Okay, pretty cool, right? That's it. All right, so again, let's recap here. A lot of ideas going on here. So we started off with the idea of continuity at a point. So we said that a function is continuous if we find the limit, right? So we're looking from the left side, from the right side, does that have a particular limit? And if that limit is equal to the actual value there, then it's continuous, right? So we found all the places where it was continuous and where it was not continuous. Then we looked at the types of discontinuities, the removable, the jump, and the infinite. And then we said the weird thing about functions and the continuity over an interval is that it could be discontinuous at some point in there, but still be continuous over the interval because of the domain of the function. And we showed it with the function 1 over x. Okay, and then we talked about compositions and continuity. So if we know that each part of a composition is continuous, then overall our function is continuous. And then lastly, we ended up with an intermediate value theorem. We said that for a continuous function over an interval from a to b, that the function takes on all values between f of a and f of b. And we ended up with a little bit of that idea to show that there is an answer to this problem. There's got to be an answer to this problem because of intermediate value theorem. All right, so if you have any questions, please bring them into class. We can talk about them and go over them. Good job today.